In the previous part of the talk, we reviewed some evidence that even 8-month-old infants have a sense of righteous punishment. In this part of the talk, we'll tell you about some new research we've been doing on the sense of punishment. Punishment is a crucial mechanism for maintaining cooperative, moral group behavior. The work I'll be telling you about has been done by Torin Liddell and myself. We examined freeloading in a public goods game. As a real-life example, consider a typical student group project in which several students contribute and they all share the same grade. The problem is that not everyone might contribute equally. In fact, if you look on the internet, you'll see this definition of a group project: it's time to relax while you watch someone who cares do all the work. Now, that would be a case of freeloading, and we might want to figure out a way to punish the freeloader. But what if the freeloader accidentally failed to contribute? What if the freeloader, for example, had a broken leg? In our novel public goods game, there were accidental contributions and different sorts of punishments. On the left, we see 3 players in this game, A, B, and C. They're each allocated 10 points at the beginning of a round, from which they have an intended contribution to the public good on the right. Then a random accident happens, perhaps a miscommunication with a broker, so that the actual contribution could be somewhat different than the intended contribution. Then the public good is multiplied by a constant, and the public good is divided equally among the 3 players. Then there were 2 possible punishments that the players could mete out to others. It could be a fine, a costly fine in which you subtract points from the others at a small cost to yourself, or you could ostracize the others. Here's what it looks like from the player's perspective. At the beginning of a round, you have 10 points. How much would you like to invest? Suppose we enter 6. Here we see the contribution table. So far, you've contributed 6. Then the accident happens. And we see, oh, actually you invested 10. After your investment is shown, then the other players appear. In this case, there were 4 other players. They made their contributions. The table shows the payoffs, the equal payoffs to everyone, and then the total gain. The total gains can be different across people because some people contributed more than others. Then there's the opportunity to punish. You can exclude another player, you can deduct points from another player, or apply no penalty. Here's a close-up. This is player B. They intended to contribute 3, they actually invested 6. That was their payoff, and at the right you see you can exclude, deduct points, or have no penalty applied. You decide whether or not to punish each of the other players, and then continue, at which point you get to see what the other players have done in terms of punishment, including whether or not they've punished you. Punishments applied to you are shown at the top in the yellow. In this case, no one decided to punish you. When players are deciding how much to punish others, this is the information available. There's the intended contribution of the other player, there's the actual contribution of the other player, and then there's the amount of total gain the other player got relative to your own total gain. We call that difference jealousy. So the extent to which they got more than you is another bit of information. We use these 3 bits of information as regressors to analyze the probability you will punish other players and what kind of punishment you will choose. Here are some fictitious data for a player. On the vertical axis is their intended contribution. On the horizontal axis is the actual contribution. Each dot is a combination of intended and actual, and the color of the dot indicates whether no penalty was applied or a punishment was applied. You can see for these fictitious data, at the top there tend to be no penalty applied, but for points lower down, where they're red, there's a punishment applied. We can summarize that by the line that goes across the dots. That's the 50% line. Above that, there's less than 50% probability of punishing. Below that, there's greater than 50% probability of punishing. And The angle of that line is summarized by the vector components labeled beta sub int for intended and beta sub act for actual. You can see in this case, as you descend on the intended contribution axis, there's a rapid increase in the probability of punishment, so beta sub int is large. However, when you descend on actual contribution, there's only a small increase in the probability of punishment, so beta sub actual is small. Here are some other fictitious data, in which case when you descend, that is, go to the left on actual contribution, there's a rapid increase in the probability of punishment, so beta sub actual is large. But in this case, when you descend on intended contribution, there's only a small increase in the probability of punishment, so beta sub intended is small. Notice both those components are negative. They go in the negative direction, meaning as you descend in contribution, you increase in the probability of punishment. Here are the results in terms of those beta weights across people. On the left, we have results for when people excluded, and on the right, we have results for when people fined. Look at the bottom. This is the beta weight on jealousy. The blue distribution describes the credible values of that beta weight given the data. We see in the lower left that it's positive. This means that as jealousy is increased, as other people got more than you, the probability of punishment went up. And that's true for whether the punishment is exclusion or the punishment is fine. So to summarize in the text here, higher jealousy leads to higher probability of exclusion and higher probability of fine. It's as if jealousy is a trigger for punishment. Now, for fines, there's a greater influence of actual contribution than intended contribution. The yellow box on the right highlights the beta weights. On the top, the beta weight for intended contribution, which is modest, and in the second row, there's the beta weight on the actual contribution, which is a large negative value, meaning if the actual contribution is low, there's a rapid increase in the probability of fining. Low actual contribution elicits fines almost regardless of intention. This is sometimes called outcome bias. For exclusion, on the other hand, and this is news in our design, for exclusion, there's a greater influence of the intended contribution than the actual. So in the upper left, we see the credible weights, beta weights on exclusion. There's a large negative value, meaning when the intended contribution drops, the probability of excluding goes up rapidly. But the beta weight on actual contribution is relatively weak, meaning that as the actual contribution goes down, the probability of excluding rises only modestly. We could summarize that by saying low intended contribution elicits ostracism almost regardless of the actual contribution. Implications for theories of punishment. In the moment, in the process of making a decision, these process models need to incorporate differential weightings for different punishments. On a longer time span, within a lifetime, another experiment we've done shows that group norms influence the application of exclusion. There's learning of punishment norms. And across generations, evolutionary theories need to incorporate sensitivity to intention as well as to actual outcome. Finally, different perspectives on intended and actual actions may lead to different moral judgments and to different punitive decisions. Please proceed now to Part 4.